grams of this compound, which is known as salicylic acid, is added to 110 grams of acetic anhydride, right? And then 105.6 grams of aspirin are produced. So what are we going to do? What are we even doing in this thing? Is there any questions? Calculate the percent yield. Oh, there you go. So what is the percent yield? Oh, right here. Okay. So that means we have to know all kinds of things to do this problem, starting with balancing the equation. How do we balance an equation? Well, we have to have the same number of each element on both sides of the equation. So on this one, because it's complex, here we have 7. Let's just break it down. So the first step is to break it down, right? So we have 7 carbons, 4 carbons, that's 11 carbons. What about this side? 9 and 2, so we have 11 carbons there. Good. 6, 12 hydrogens. Does everyone see that? 8 and 9 and 3 is 12 hydrogens. Oh, this is looking good. Oxygens, 3 and 3, that's 6. 6 oxygens. And then 4 and 2, that's 6. So we have the same number on each side, which means we don't have to do any balancing. It's already balanced. Yay! Yay. So the way we read this, how do we read? We read the equation. Is the next step, right? And what we say is we say for, if there's a number here, that would be the number we would say. But this all has ones. So we're going to say 1 mole of salicylic acid, or C7H6O3, plus 1 mole of C4H6O3 yields, right? This is our yield, our arrow, our equation arrow says yields 1 mole of C9H8O4 plus 1 mole of HC2H3O2, or acetic acid. Okay? That's how we say it. So for every, and this is our mole number, right? And we'll talk about how we get there in a second. So 1 mole of salicylic acid plus 1 mole of acetic anhydride yields 1 mole of what? Aspirin, and 1 mole of acetic acid. Okay. Now, we're given these grams amounts. We say we have 104 grams of salicylic acid and 110 grams of acetic anhydride. And we're going to make 105.6 grams of aspirin. So how do all those things tie together? Well, that's how we have to develop our understanding of what makes things equal. And what makes things equal is the number we call a mole. Okay? And the good thing about a mole is that it allows us to compare different masses of different elements, add them together, and still have the same ratios, whole number ratios all the way across. So, we talked about atomic mass today. So, one of the next things, we read the equation. Now, how do we determine the mass of a mole? All right. So let's just start with carbon. How do we get the mass of carbon? Periodic table. And what is the mass of carbon for 1 atom of carbon?
12.01.
12.01.
Right. 1 atom of carbon has a mass equal to what? 12.01 atomic mass units. So 1 atom of carbon has 6 protons, 6 neutrons, 6 electrons. Electrons have no mass, so we're just looking at the mass of the neutrons and the protons, and that gives us, in one atom, 12.01 AMU. But we aren't just putting one atom together, right? We're putting masses together. So we can't use AMU because we need to use amounts we can measure. So what we found out is that if you take 6.022 times 10 to the 23rd atoms, we're going to give that the name of 1 mole of atoms. So anytime we talk about a mole of atoms, we're talking about this many of them. Well, that's kind of a lot to really keep track of and to put in your calculator every time you want to do something. So we said that 6.022 times 10 to the 23rd atoms, or 1 mole, is 1 mole of carbon atoms is 12.01 grams of carbon. So without doing any of the conversions that we're going to do later, we can get directly to the mass. Because if we say we have a mole of carbon, it's 12.01 grams. So if 1 mole of carbon is 12.01 grams, how much is 1 mole of hydrogen atoms? What is its mass?
1.0.
Right? What if let's now go, what if I had, let's keep going. What about 1 mole of oxygen?
Oxygen is, well, it's 15.999.
All right?
Yeah,
Okay? So, anytime we need to know how much a mole of what?
in this table, it says 15.999. In the lab book table, it just says 16.
Right. What happens if you round off here?
16. So one
Yeah,
of the
one's a little bit more precise,
Yeah.
and then it gives us a flexibility of 100th. This one only gives us, 1,000th, and this only gives us a flexibility of 100th. Either one is correct,
Okay.
right? Because to 4 places, it's the same, right? If you're using 4 significant figures, this is still 16, right? Because you're going to round from here. Okay. And you will find little variations and fluctuations in periodic tables based on their taking liberties with their significant figures. Okay? Oh, hold on. What is this one? We have this big one too that we use sometimes. I like to dance in front of this one. Right, it's a valid question. See, look, this one is 9994, right?
That's even more.
Yeah, even more, 10 to the 10,000th. All right? So we'll leave that up. Give me a barrier. Stay safe in case the crowd revolts. Okay. Oh, but then you can't see the floor. All right, we'll just put this back over here.
No blocking for you.
You tried.
Anyway, so we have these 3 now. What about if I said how much is a mole of platinum?
195.1.
Okay, how about a mole of uranium?
That's all you.
238.
Yeah, 238, U238. Okay, and then what about a mole of fluorine?
19.
Yeah. Okay, so we're getting the idea, right? All you have to do to get how much a mole weighs is look at the periodic table, the atomic mass, right? And then, but we don't say it the atomic mass. We say it's a mole mass, and the mole mass is grams. All right. So now, what if I had 7 moles of carbon?
You just multiply it by 7. Multiply by 7.
Yeah, anybody didn't disagree with that? Or, no, because we're just taking this 7 times, right? If we have 7 moles, you just multiply it by 7, so that would be, what, 84.07?
Yes.
Everybody with me? Grams of carbon. What if we had 6 moles of hydrogen?
Do the same thing. Multiply by 6.
Yeah, multiply by 6 times 1.0078. And that's like what, 6.0048? Right? And then what if we had 3 moles of oxygen?
Multiply that by 3.
Oh yeah, let's do that. I'm already, this is not my new one, is it?
Lead 'em horse to water.
But you can't make them use a pen. 15.999 grams of, right? And so what, that is 40, what is that, 48?
That is
48.
47, oh, yeah, 48.
Close enough, right?
47.997.
Okay. So we determined that if we have 7 moles of carbon, it's 84 grams. We determined if we have 6 moles of H, it's 6.04048 grams. Did I have too many zeros? I did.
Yeah, you do. And it's actually 6.8.
6 what?
I believe it's 6.068.
Oh, okay. 56 plus, yeah,
Is that
could be.
7?
Did someone do this?
7, 8 times
42 plus 48?
6.0468.
Okay. All right. So we're getting more precise with this, right? Because I just did an estimate in my head. What about this one? Is that one still good?
Yep.
All right, so we have 7 moles of carbon, 6 moles of H, and these are the weights of each of the components. Now, if we come back here to our starting material, our salicylic acid, we find that's the formula for salicylic acid. So in order to know the weight of 1 mole, we add up all the components. Okay, so what would be the mass?
One
138 point.
zero. I'm not processing. I rounded up a lot.
0.1138.
0.1138?
Yeah.
1138 grams. And then we would say C7H6O3. Now, that's equal to you guys see that? Right? So in order to calculate a mole of a substance, we take all the component moles and their masses, add them together to get a final number. This information right here will allow you to synthesize anything that you know the formula of. Well, I mean, there's some other steps too, but it's like the key to the palace, right? If you could figure out how much something weighs, how much a mole of it is, how many of each go together, you can build anything. And that's what people do. And now that's what AI does. So that's 1 mole of this. So for 1 mole of this, it would be 138.1138 grams. How much do we have? 104.8. Is that a mole?
No.
No, it's not enough. It's less than a mole. But I thought we went 1 mole to 1 mole. Well, we do. But we can also go parts of a mole to parts of a mole. So the next step would be to see how many moles we have. Right? So how many moles? salicylic. That doesn't look right. Anyway, we have 106, what do we have? 106.4? 104.8. 104.8 grams C6H7O. C7H6O3. Right? Okay, so can you give me that number?
0.7588.
All right. So, turns out that we just calculated the mass of a formula, right? We turned it into the number of moles of a formula. Then we took an amount that we have and we turned that into a number of moles. That number of moles is 0.7588. So in order to use up 104.8 grams of salicylic acid, right, we have to go to the next component or reactant, right? So reactants on this side, products on that side. We have one reactant that has 0.7588 moles. We know that we need to use 1 mole to 1 mole. So how much of this do we need to have in order to use up all of this?
0.7588.
Anyone else? Going once. Anyone else want to guess? How much do we need? It's a 1-to-1 ratio, and we have 0.7588.
They think exactly the same, 0.7588. 1 to 1.
Yeah, 1-to-1. So in order to use up all of this, we have to have the same amount of acetic anhydride. Anyone not see that? Right. So if I had 1 mole, I could use 1 mole. If I have less than 1 mole, I need less than 1 mole, at least. I could have more than, in which case I wouldn't use up all of this. All right, so that was our first calculation. Now we're going to do the same thing for the other one, right? And we already have all this, so let's leave this the same. We'll get rid of this. And we're just going to change these numbers, right? C4. You're going to have to write more than me on this one. Oh, well, look, this one stays the same. And that one stays the same. Oh my goodness, this is just too easy. So we have to change this number. This becomes 48.04, right? And that changes this number. And what's our new mass for the acetic anhydride? Did I lose anybody there?
No.
What is this number?
102.0838.
102.0838.
Yeah.
Okay. Haha. What can you see already?
gonna be greater than 1.
What do we have here? How much do we have?
110,
110 grams. How much is 1 mole?
102.
102 grams. So, do we have enough to use up all the salicylic acid?
You should.
Yeah.
About 0.7588.
All right, well, yeah, exactly. So keep that in mind. And now, let's take how much we have. 110.8?
9.
110.9.
Oh wait, it says 8 on our paper, but homie wrote 9 on the board.
Don't worry about it. Just bookkeeping error.
Oh,
No, it's 110.9.
why does mine say 8?
Which one are you
Yours
reading?
says 110.9.
Keep going.
110.9.
Oh my God. That's what I get for trusting people. All right, here we go. We go, Vin.
No. Just revoked.
Grams C4H6O3 divided by, what did we get? 102.0838 grams C4H6O3. All right. And that comes out to 1 point something.
1.0864.
Do we have confirmation?
That's right.
Nate's trustworthy.
We just got burned on trust. We're done. We trust and verify now. It's like we're school children, right? C4H6O3. So which one do we have more of?
Acetate anhydride.
Yeah, the acetic anhydride, right? We have 1 mole of that, but we only have 0.758 moles of this. So which one's going to run out first,
The salicylic acids.
right?
Yeah.
That's the limiting factor then.
Right. So runs out first. So the most that we can make is 7.588 moles of aspirin, right? Because it's 1 mole to 1 mole. Okay, so runs out first. We call running out first limiting. Okay, so now we're going to take this number of moles that's possible to make, and we're going to see how much a mole of this weighs and how much we make. Right? So the next step then is to do the same thing that we just got done doing. And this is what we do all day long, right, in this class. So we're going to change this now. Our next calculation is going to involve C9H8O. C9H8O4. All right, so 4 moles of oxygen this time. And this problem's great for this because you just have to set it up once. What is 9 times 12, 108 or something?
Sure.
0.09.
Is that right?
Yeah.
0.09?
Yeah.
All right.
Thanks, Lon.
And then 8, this one's a little bit different a little bit. You can change this whenever. But is anybody not seeing what we're doing? Because now's the time. We're gonna go over it again in lecture, but right now is the time to go, I can't just write this down, I have to know what's going on, because we're gonna be doing this over and over and over again. And then, but you have a chance though, if you're quiet, because we're gonna do it again next problem. And we're gonna keep doing it until I get to a point where you guys are telling me how to do it. Right? So that may take 2, may take 3, may take 4 problems. But at some point, you're gonna be doing these on your own for the rest of the day. So, ask away your questions. Did we get a number for this? For each part of it, I should say.
It's 0.5878. For the whole answer.
And what is this? This is like 659.994. Is that right? No.
No, I got 64.
63.996.
Oh yeah, because it's 16, huh?
Yeah.
What is it?
63.996.
63.996? Yeah. All right, and then our total is
58 or 0.5878.
I got 180.1484.
180.1484.
Yeah, but that hydrogen one's incorrect.
Yeah.
It's 8.0624.
We just sit there and let me do that, huh?
Sorry,
It's all right, Nate.
letting it ride.
It's all right.
Oh, no, I skipped the part. I went too far.
All right.
No.
So we need 180 grams to make a mole, right? And we made what? 105.6. All right. But that's what that's what happened here. So this part isn't right.
We haven't
That
done
part's
it.
not right.
Haven't
We
done
haven't
that
done
yet.
it yet.
Oh yeah, we haven't got to this part yet.
Yeah.
We're just right here.
Yes.
This part was right. Gosh darn it. Well, doesn't matter though, we don't need this anymore.
Like the last time.
This is what happens when you don't have enough boardroom. This board should just go all the way around the class. All right, okay, so we're here. This is limiting. Let's rewrite that up here. 0.7588 moles of C7H6O3. All right. So it's possible to make zero point 0.7588 moles of C9H8O4.
C7H6. Right. That was the first one.
Right. So, but it's also possible if we use up all of this, because it's 1 to 1 to 1 to 1, that if we use up 1 mole of this, we make 1 mole of that. But if all we have is 0.7508,
That's all we get.
all we can make is 0.7508 of the product.
Even if that one's less than 0.75.
You could only make as much as you, like if this was less than 0.7588, you couldn't make 0.7588 of this. Even though this one's, so if you were just looking at the acetic anhydride, you could make more than a mole because our number was greater than 1. But because you have to have an equal amount of reactants in terms of moles, not in terms of weight, right? We're limited by this amount, which is 0.7588.
Okay.
So we can only make 0.7588 of this. We're gonna make less, but we could make up to that much.
Okay.
And when we say how much we could make up to that amount, this becomes the possible to make means theoretical. Theoretical yield. Okay? You with me? All right. So our theoretical yield is 0.7588 moles of aspirin. We know that a mole of aspirin weighs this much. right? So if we want to convert, a lot of times we want to convert, right? So we want to convert from moles to grams. And this is why we do all the conversions. To what, grams? We put grams on top. And that's what I remember, 180 grams C9H8O4. Right? And now moles cancel. And I'm left with a gram amount. And what does that gram amount do? And every single one of you should be doing this on your calculator if you can. Right? And slow me down so you can write it all down.
Question.
Yes, Sydney.
Why are we changing back to grams? Because we're finding the percent yield, can we just keep it in moles?
Well, you'd have to convert to moles then. Right? We're already in
Convert the
grams,
aspirin
so,
to moles? Is that what you're saying?
I'm sorry?
Convert the aspirin to moles?
Yeah, you'd have to convert that to moles. So I just as soon convert my theoretical yield into grams and then do a gram comparison.
But it should still be the same percent if you do it in moles over moles or grams over grams.
Yeah, it should be.
Yeah. Okay.
So do we have a number for this yet? Why don't you do it that way and then we'll compare. I would do it, but I gave my calculator away.
She just said that.
So 136.6966.
Yeah?
Mm-hmm.
Okay. So what we call this then is the, what is this still? Theoretical yield. All right? So we could make as many as 136.6966. But what did we make? 105.6. So this is called actual yield. So the actual yield, and let's put that down too. 105.6. Is that 105? 105.6. Grams of C9H8O4. And you know what? You've probably written this down enough times now that you know that aspirin is C9H8O4. Probably. Actual yield. And then $136.6966 grams is the theoretical yield. And I'm just going to call that theo. And then times 100%. So how much did we make?
77.25.
Percent?
Yeah. It keeps going, but.
And you got it going the other way, right?
Yeah.
So again, there's multiple ways to do this. As long as you do it and you're comfortable with your method, that's fine. This is the method I'm showing you. That's it. Okay, so what happened here? What happened, let's recap, right? We start off, we didn't know anything, right? All we knew is, here's some letters and numbers, and here's some more, and here's some more. We know that the reactants are on this side, and the products are on that side. We learned that we count the number in front if there is one, but here there's only one. We say 1 mole of reactant A plus 1 mole of reactant B yields 1 mole of product A and 1 mole of product B. To be more specific, we say 1 mole of C7H6O3, which turns out to be related to what we call the molar mass, or just adding up all the elements and their masses to tell us how much grams we need to make a mole, so we can do our comparison between different weight objects, right? We found out that that has a certain mass, and that this number that we were given is a percent of that mole, and that whatever, okay, let's slow down. I was doing well. So 1 mole plus 1 mole is 1 mole plus 1 mole, good. Add up all the weights, you get a mass, a molar mass, right? You find out how many moles of product A you have, or reactant A you have. You find out how many moles of reactant B you have. Whichever one has the lesser amount is the limiting reagent, right? Especially in a 1-to-1 ratio. It's very easy to tell, right? This one made less than 1, this one made more than 1, so this is going to be the limiting reagent. And we're going to calculate the molar mass for each of the items of interest or compounds of interest, and then we're going to compare them, right? So we got our limiting amount of moles, and we said since it's 1-to-1, we have 1 mole of reactant, we make 1 mole of product, so it's only possible to make 1 mole of product. Based on this calculation, we can only make 0.7588 moles. That becomes our theoretical yield. How much we can make is our theoretical yield. Go ahead.
How can we find out the molar mass of HC2H3O?
That's a great question. Why did we ignore acetic acid?
Because it's a byproduct, and we're not looking for it.
That's a great answer. Yeah, we didn't need it for our calculations, right? We could have, right? We could have found out, we can find out exactly how much is left over too, right? But we don't need this to calculate how much of this we made.
Just looking for aspirin.
Yeah, we were just looking for aspirin. If it said how much of each product was made, now we'd go back and do the same calculation for acetic acid. But fortunately, they didn't make us do that in this problem. All right. So we got our theoretical yield, which is how much we could possibly make. Then we have our actual yield, which is how much we did make. And I like to convert from moles to grams. I always like to go, my thing is to go from grams to moles to moles, moles to grams, or GUMGA. Grams to moles to moles, moles to grams. And very few people say GUMGA, but I do. All right, and so we're going to take our actual yield, divide by our theoretical yield, and multiply by 100%. Okay? So that's a lot right there, especially since we haven't even introduced any of those things. That's problem 1. Now, can I get someone to write problem 2 up here while I take a little breather? That's my breath. Please. Vince, you did a great job if you want to do it again.
This one's a bit shorter, so.
Uh-oh. And don't worry, we're going to introduce this. We still have several weeks of looking at this material, so I don't expect you to have it down today. All right? We're just introducing it. We're introducing the whole thing, and then we're going to break it down into its individual components and do it again.
Are there ever cases where the two beginning are the same amount?
Excuse me?
Are there ever cases where these, like say for instance, they were both 0.7588 moles, and then you would just pick one or the other?
Yeah. Well, yeah. If it's that case, they're both the limiting reagents. It doesn't matter, right? But most of the time, we set them different so that you have to pick.
Okay.
So you have to calculate both of them, or all 4 of them, or whatever. Yeah. So. But in the best synthesis, you're going to want you're gonna use, the limiting reagent's gonna be the most expensive one, right? And then the other one, you're just gonna throw a little bit extra in, to make sure it all complexes.
So it's like this, the 2 and a, and that's 9. Is this 2 represented for 2 sodiums and 2 iodines? Or is it just attached to the sodium? 2 of whatever. It's also 2 of those.
You have all the good colors too, Maria. These are all the good colors. These are the good colors. A lot of times, you put in a bunch of colors you don't want. These are the good colors. What's that?
Why don't you just throw in old markers,
So you know
you
what
use.
Genius.
That's a good point, huh?
Or put them aside.
I'm not letting anyone else use my good markers.
Put them aside for the other teachers and then use just.
Yeah, just leave those and then keep mine. Boy, I'm so selfish. No way to run it.
2. I'm gonna write number 2 here.
That giant ego cover.
Was that? Oh, it's just yeah.
6, 7, 8.
It's more simple. It's not kind of divide by.
Are you, maybe I should just tell you what to write down, because you write so much nicer than I do. I like that.
I didn't write it for you.
People can read it.
This is literally what we were doing a lot. Chemicals and like the moments of them. And they were way out. Chemicals.
That was good.
Yeah.
What is the actual yield? Percent yield is 66.9. Yep.
It's all yours.
Thank you, sir. Okay then. So, we're going around the room now, and I'm gonna ask questions. Dom?
Are we to assume everyone on here is already balanced? Or are we
No,
gonna check?
no, that's the first thing I'm gonna do. Actually, great lead in. Thanks for being here.
He says they're all balanced.
No, just the second problem.
Oh.
I don't know about
So, let's find out if it's balanced, okay? Maria, how many NAs are there?
2,
2. And how about on the other side?
2,
Good, so that part's balanced. Brittany, how many B's are there?
1, 2,
Right? Remember, this 2 in the front, the coefficient distributes all the way through the whole thing. Right?
it
So,
is,
so how many B's?
2,
Okay, and then on this side?
2,
Good. All right. Dom, how many H's on this side?
Would I add 4 to it, or would I just say 2? So it's only 6 then.
4 times 2, wouldn't it?
Oh, okay, 8.
8, good. Now on this side?
6, I can't. 8, okay. I'm blind, I can't.
Oh, you can't read that? Okay, well, it's on here, dude.
Yeah, oh, yeah. I know what you said. 8 is that.
Hey, all right, we're good. So remember, it's not about getting it right.
I'm looking
It's
at
just
it.
about having a good time. We're just having a good time. We're talking about chemistry. If you feel good about something, it's so much easier to remember it than it is if you're stressing about it. I'm just saying, okay? It's okay to make mistakes. You caught me making mistakes. It's good. You catch me making mistakes so that you can justify making some mistakes yourself if you need to, right? And then argue with me if I mark something wrong and you think, well, you made a mistake before. You could easily have graded this incorrectly, which is usually the case. Okay, we have 1 left. We have I2, and then Ben, how many I's are there on the other side? 2. Okay, so we're balanced. We've covered all our elements. Our equation's balanced. We always check first, because sometimes if you do a reaction and it's not balanced, the numbers don't work, and that's a problem. Okay,
Then you're almost.
so we have this, and what are we given? How do we say this? we say 2 moles of sodium borohydride plus iodine in, oh, what about these? Right, these are the states. So this is sodium borohydride solid, iodine solid,
Gas.
Gaseous.
yeah, gaseous, yeah, or gaseous, right? Borohydride plus
Solid.
solid sodium iodide plus H2 gas, okay? So that tells us what's happening. This is what we call a gas evolution reaction because gas comes out, okay? And it's a hydrogen gas evolution reaction, even more so. So what's our first step? Oh, we've set it 1.023, oh, it's right there. But he changed this form.
What I do?
Did I already lose one of the good pens already?
No, it's right there behind you on the desk.
Yes.
No, I already lost one of the good pens.
There's another black one to your right.
It's gotta be this one though. That's not the right brand. I killed it. I already used up the whole pen. 1.23 and then excess. What does excess mean?
What's left over?
Let's go.
Yeah, excess. There's more than enough. So we don't even have to calculate anything with I2, right? Because it's in excess, which means there's more than enough to go around. Whoopee, we don't have to calculate that, thank goodness. Okay, and then we're not given how much of the product of interest that we made, right? Because this is what we're looking at, right? What is the actual yield of borohydride? Yeah. So let's put that there. So, what did we do before? What's the first step? Grams to moles,
Yep.
right? Well, we don't have the moles of sodium borohydride, so how do we get that? What does sodium weigh? 1 mole of sodium.
22.99.
99?
That's what I got in the lab book.
Yeah, 22.99, yeah.
Okay. 1 mole is 22.99 grams. We only have 1. How about 1 mole of boron? Oh, who's next? Who's after Ben? How much is 1 mole of boron weigh? 10? We gotta have more digits. Do you know?
10.81.
One more time?
10.81.
Okay, thank you. And then hydrogen, we know, so we're gonna skip that one. But you know what we're gonna do next is calculate the total mass, so whoever gets, times 4, right? This is times 4. 4 times 1.0078 grams each.
Yes, times 8.
So,
Is it not times 8?
is it times 8?
I guess you can
Oh,
multiply everything
no.
times 2. at
Oh,
the end.
perfect. So Nathan just brought up one of the common pitfalls. A mole of sodium borohydride has nothing to do with the coefficient.
Okay.
It's always just 1. The coefficient is what we call the stoichiometric amount, which means for every 2 moles of sodium borohydride, we use 1 mole of iodine, and we make 1 mole of this borohydride, which I don't know the actual name of, so I
We
just call
wouldn't
it
use the
both
2 at all,
borohydride.
like to divide it in the end. You wouldn't need the 2, just leave the 2 out at all.
You leave the 2 out altogether. It's only used when you're using the ratio, which means you have to have twice as many moles of sodium borohydride as you do I2, but it doesn't change the value of 1 mole of the compound.
Right.
1 mole of the compound is always just the formula molar mass. So I've been stalling. Are we getting close?
Yeah.
Is these periodic table and your periodic table have variations?
I got bad hearing.
37.8.
37.832. Alright,
So on your hydrogen, how did you get the 1.0078 if the periodic table says 1.008? Like I'm lost on that one.
okay, so if I have one more here
Uh-huh.
and I round, that becomes 1.08. So that's just one of the ones I know, because
I see.
We could use either or. Though,
You could
right?
use either
Because
one
some
of
tables
those.
are different.
there's no difference. I just have one more significant figure, that's all.
Okay, thank you.
You're welcome, a great question, right? If you ever have a question at any point, don't do what I did with my emotional health, right? Don't just make an answer that fits the situation and then keep using it long after. Find out why, right? Believe me, and if you start doing it now, by the time you're my age, you might have some good math skills. I don't know. All right, what did 37 point what? 832 grams for the sodium borohydride.
So how come we don't use 4 significant figures instead? Are we still using significant figures?
Yes, but only at the very end, right? This is just for our calculation. So I'm not going, but what I'm noting here is 4, right? And I note here 4, right? So when I get to the end, I'm going to have 4, right? That's a great question. Okay. All right, why did we do that again now?
It's how much sodium.
What do we do next? So we found out the molar mass. Now we have to take grams to moles. So we have 1.023 grams NaBH4 times 1 mole.
1.203.
1.203, yeah.
Oh yeah. Boy, dyslexia too. All that on top of that. NaBH4. But you see me, I'm not going to worry about it. I'm just going to keep moving forward because not much I can do about it after starting the problem. Grams NaBH4. Okay, that leaves this calculation to you, Emmanuel.
0.03179.
Moles. Oops. Boy, I'm getting sloppy now. All right. And we did, whoa! Okay, so we got 2 here, 1 here. So how many moles is it possible to make of this?
0.3179. 1 to 1.
Is it 1 to 1?
Oh, no, it's not, it's 2 to 1.
It's 2 to 1.
Ah, so that's.
So
where that-
I can only make half as many of these, right?
Why, can you explain that? I don't get that.
That's where.
Okay,
That's
so
where that 2 comes.
if this 2 wasn't here,
It'd be 1 to 1.
1 to 1. And so I would be able to make 0.3179 moles of,
Point zero.
It's 0.03.
0.031.
Yeah, it's 0.03179.
well, if you're not making mistakes, you're not doing anything. All right, here we go. Which is why I don't like canned lectures. Nobody makes any mistakes. Anyway, 1 point. Don't have to worry about that here, though. Here we go. 0.03179 moles of sodium borohydride.
If it were 1 to 1.
If it were 1 to 1. But it's not. Takes 2 of these to make 1 of those. So our ratio then becomes 3.03179 moles. And this is where we go from moles to moles, right? And where do we get that ratio? And again, I don't expect you to know this yet. Remember, we're introducing the act. All right? So we have moles of 1, we want to get rid of it. And we want to go to the moles that we're making. And now, regardless of what this is, right? Our number here is 1. So we're just going to put a 1 here. Our number here is a 2. So we're going to put a 2 here. So for every 1 mole that we make, it takes 2 moles of reactant. And whatever these numbers are, if we were making sodium iodide, it'd be 2 to 2 ratio, right? You see that?
Yeah. Flipping two.
Hey Vince, can you do this 0.3179 divided by 2, please?
Like 0, 1, 5, 8, 9, 5.
If it was a 2 to 2 ratio, would you times it by 2 then?
Yeah, you times it by 2 and divide by 2, right?
Yeah.
So it'd just be 1.
So that would just be
Got it.
one then, goes to the 2.
But yeah, but that's where you get the numbers for this conversion.
Yeah.
I don't want to mess it up by making it like 5 to 6, but it's the same idea. Whatever the number in the front is, that's what we use for the conversion.
Am I the only one who got .0158?
I got
Yeah,
that.
I have 0.0158.
5895.
Yeah, yeah. Okay, not bad.
158.
Yeah,
15895.
Okay. We'll just leave it. And then that's our moles of B2H6. Okay. All right. So, what is this number?
How much we got at the end?
Oh, no.
Is that the fraction?
Then what?
Oh, no, that's the theoretical.
I heard it.
Theoretical.
Theoretical yield. Right? Because we started with,
So if you do everything perfect, that's what we should get.
right. But if you set it up close, right, you're going to get most of the points. Grams to moles. Moles to moles. And now we're going to go back to grams. And that's, Sydney, that's why you usually, you can use moles to find out limiting reagent, but usually everything else is in grams. So either you're going to have to go from grams to moles at the end, or just go back to grams all the time, which is the way I like to do it. Doesn't mean you have to. Okay, so this is our moles. This is our theoretical yield of moles. So Theo. All right, what else are we doing now? We got a percent yield, so we could actually stay in it, but let's go back to grams, right? So we have to calculate the molar mass of B2H6, which would be, we already know 1 mole of B is, so this is 2 times 10.81 grams of B. And then what else do we have? H, and we have 6 of those. 6 times 1.008, so everybody doesn't freak out. And here we go. That falls on you, Priscilla. And you can just give me the total, you don't have to break it down. 27.668 grams B2H6. All right, so that's in a mole, right? All right. So now let's convert our moles of B2 0.015895 moles B2H6 Okay, rid of moles of B2H6. Remember, and whenever we're doing moles, it's just one of them, right? And 27.668. Kylie, what do we got?
0.4398.
All right. So that's our theoretical yield in grams. All right.
Is that our actual yield? Oh wait, never mind, sorry.
No. All right. So then the next question is percent yield equals actual over theo. Notice I'm taking shortcuts now. 100%. Right? And we're given percent yield is 66.9%. So, and our theo is 0.4398 grams. And that means we have to calculate actual times 100. So if we divide by percent, right, we get 0.6698 equals, oh, let's just do the whole thing, times 0.4398 grams B2H6. What I got there? Equals actual. All right, and then that goes to you, Jordan.
Give me a second.
Yeah, no worries. Everybody see what I did there? So.
How did you get the 66.9%?
It was given.
Oh, given. Yes, it was.
I got 0.29457. 457.
All right. 2 down.
I thought we had to do 4 significant figures.
Oh, yeah. Good point. Now we go back and do our significant figures, and this is a good one because and we didn't have to calculate the sodium or the hydrogen, right? The sodium iodide or the hydrogen. So that was nice. Questions? It's good stuff today. Really good stuff. All right. Uh-oh. So I'm going to do this one. Let me take a minute here. So for those of you that are lost, right, you're building new circuits in your brain. And don't worry about it. Because we're going to do another one. And then we're going to do another one. And then by the end of the day, you'll have done 8 of them. Hopefully at some point, I won't be doing it. Okay, so Nathan, you're next.
I'm next?
No,
There's two Nathans.
there's two Nathans.
Easy.
And you get an easy one. Now wait a minute. Alright, just do the whole thing. Right. And if at any point you get so far behind you can't you can't write it all down, take a picture and then translate. Okay. So aluminum metal. So that's aluminum solid plus, I'm not gonna try to color coordinate because that doesn't work. Okay. Solid iron 3. So what's the charge on the iron? 3 plus, right? So let's just do this one on the side so that we know that we're on the side here. And then we'll put the full compound on the top. So iron 3 plus, what's the charge on oxygen?
-2?
Correct. O2 minus. Those go together, right? So if you just put it 1 to 1, the overall charge would be what? -1. So it's -1, so, I mean +1. Because you have 3 plus, 2 minus. So let's add another oxygen. Now your overall charge is -4 plus 3 or -1. Okay, so let's add another iron. And now it's FeO2 4 minus, right? So that's 6 plus, because we have 2 of these, right? 6 plus, 4 minus, that's 2 plus. So we add 1 more O2 minus, and that gives us 0. So 3O2, 3O, and 2 Fe. Right? That charge balances to 6. So here we go. FeO3, and what is that? Is that a solid? Yeah. And that's going to yield. I really did use this. This is the bad one. Oh well. All right. And that yields what? Solid aluminum oxide. Which it turns out aluminum's 3 plus, so we just repeat the whole fandango. And
Iron metal.
oh yeah, and iron metal,
Fe.
Fe. Okay, and this is a solid too. And when we write reactions, we always try to get the state if we can. Okay. So how many grams of iron are produced by the reaction of 450.14 grams of iron oxide and 99.1 grams of aluminum? All right, and how many grams of iron? Question mark. Grams. Okay, and then, oh, which reactant is limited? So we don't even have, well, we still have to do the whole thing.
It's not balanced yet.
Oh, there you go. Clever. Sneaky, too. All right, so. Did I already get you, Nathan? Did I ask you a question already?
No.
All right, so how many aluminums do I have on this side?
2.
So how many do I need on this side?
2.
I call this chasing the metal. This is how I balance equation. So now I have 2 aluminums, 2 aluminums, good. I have 2 irons. How many irons do I have?
1.
So I need
2.
2. I have 3 oxygens, and I have 3 oxygens. So now I'm totally balanced. Okay? Although that 2 is kind of, my 2s are not for public consumption. They're not good. I work on them all the time. All right, so 2 irons. So when we read this equation,
You want oxygen?
what?
Yeah.
Yeah. Yes, they do, sorry.
read this equation for me.
Read it for you?
Yeah. Two, two what? 2 moles
2 moles of aluminum
plus, how many moles of, oh, yeah,
Yeah, I didn't. Is it do I just say iron?
iron 2 oxide.
Iron 2
So
oxide.
2 moles of
2
aluminum
moles of aluminum
plus 1 mole,
plus 1 mole of iron. Right?
iron 2.
Iron. Why do you say iron 2?
It's iron 3.
It's
Spell
supposed to be
iron
iron
3
3.
first of all.
Ooh, first of all, it's supposed to be iron 3, not iron 2, right? So that's why I shouldn't say that. Okay, so iron 3, why do I say iron 3? Because we need to know the charge. Because there's 2 possibilities. There's iron 2 oxide and iron 3 oxide. And we say iron to differentiate the charges. Because this is Fe2 plus, and we write that iron 2. This is Fe3 plus, and we write it iron 3. They're both iron oxide, so you can't just say iron oxide because it could be either one of these 2.
Oh.
So we differentiate which one it is by the Roman numeral and the charge.
That makes sense.
So that's why we say iron 3. So this is 2 moles of aluminum plus 1 mole iron 3 oxide yields.
1 mole of aluminum 2. No.
We don't have to say anything for
Okay.
aluminum because it's fixed.
Okay. 1 mole of aluminum oxide plus 2 moles of iron.
Perfect. All right. Okay, so there we are. We have our equation, we've read our equation, and now we're going to use grams to moles to determine what? Theoretical yield, right? But what do we need? We need to know both of them and how much they make in terms of what are we looking to solve for? Question mark. How much iron? So, aluminum's easy to do, right? What's molar mass of aluminum? 6.98?
26.98.
Okay, and we have 99.1 grams, so 99.1 grams times 1 mole aluminum, 26.98 grams of aluminum, and that comes out to what? So 26, well, 99 divided by 26.9.
3.673091.
3.67,
3.6.
that'll work, moles. Again, I'm not concerned at the beginning, right? All right, and now, since we have to do iron 3 oxide as well, we might as well do that now, too.
It's 3.673.
3 point what?
673.
Okay. Okay, let's do this one as well. So, 2 irons and 3 oxygens. What's our mass for? Can we do that without having to write it all out?
Wait, why didn't you do 2 aluminum?
It's the
Because
coefficient.
you don't take that into account.
Because, right, the stoichiometric amount is used in determining how many moles are used in the reaction. To determine how many moles of a substance you have, you only do the mass.
That makes sense.
And then the subscripts tell you how many of that.
Yeah.
The subscripts tell you how many irons there are in the compound. The
Not
coefficient just says, coefficient has nothing to do with the moles except for how many do we use of the moles that we have, but we have moles are only based on the formula. So we do need to do the 2 irons. So 2 irons plus 3 oxygens. What is the total for that? 159.67, right? And once you know how to calculate them, right, you probably look them up.
I got 111.
What's that?
I got 111.7.
And then you
That's
add
for
the
iron.
oxygen.
And then you add the oxygen.
Oh, I didn't know
Yeah.
there was nothing.
All right, now I'm lost. So
Oh, so I gave you the
159.67. Okay, and so now we're going to take, that's our molar mass. Now we're going to take 450.14 grams of iron 2 oxide and convert that to moles of iron 2 oxide. Boy, this purple is bright. FE2. I like you though. All right. And Sydney, are you up? Who's up?
I can do it.
I would like you to.
Okay. 2.8192.
2.8912.
2.8192.
2.8192 moles. All right. If it was 1-to-1, we would definitely, well, let's just decide which one is going to be the limiting reagent. Which one do we run out of first?
Iron oxide.
Do we?
I think the iron would run out first. Well, it's,
Do we?
Less moles than the other, than aluminum.
Except for what? How many moles of aluminum do we have to use?
you have to use 2 moles.
2 times as much,
Yeah.
right? For 2 moles of aluminum, we use 1 mole of iron 3 oxide. So is this twice that?
No.
So you'd run out, you'd run out of this first, right? Because in order, you'd have to be 4.6 to be twice as much. So you're definitely gonna run out of aluminum first. But does that matter? Yes. Why? Oh, right, see, you always do limiting reagent first. I don't know why that isn't the first question. So we're doing part B, right? What reactant is limiting? It's aluminum. But why does that matter? What does the limiting reagent tell us?
It affects how much iron's gonna be made after the reaction.
Right. The limiting reaction determines how much product can be made. The limiting reactant determines how much product can be made. So do we have to even worry about this guy? No, throw it out. It's in excess. So all we have to calculate now is how much iron is made from our starting amount of aluminum. So we have, 3.673 moles of aluminum. We want to go to moles of iron, right? So we went grams to moles, now we go moles to moles. Moles of iron, 2 moles iron. How many moles of aluminum? 2. Where do we get those ratios? 2 moles of aluminum makes 2 moles of iron. So if we're going to moles of iron, we grab the coefficient. If we're going from aluminum, we also grab the coefficient. Yeah? So How many moles are we gonna make? All right, but we probably want a gram amount, because we usually want to know grams. Yeah, how many grams? So now we're gonna take 3.63 and go from moles back to grams. What is it, 26.98? No, because that's aluminum now. What is iron? 111?
Yeah.
Iron?
111.7.
Point?
Timesing it by 2.
And this would be you, Jules. We're gonna do 3.673 times the molar mass of iron.
Wait, is it?
That's 2 moles of iron.
Yeah, yeah, that's 2 moles.
111.7 is 2 moles of iron.
Oh.
One mole is 55.85.
That sounds better. Right? Two oh nine point one.
205.1.
All right. So that answers both questions.
So the limiting reactant was
Aluminum.
aluminum.
Right. And once you know the limiting reactant, you don't have to use the reactant in excess, except for sometimes, especially at this level, they're going to make you go back and say how much of the excess reagent was left, in which case you have to do those calculations too.
Backtracking, how did we get 3.673 moles?
Because of the 2.
We were given 99.1 grams of aluminum, so we converted grams of aluminum using the molar mass of aluminum to get the number of moles of aluminum. Then we use the ratio right here, 3.673 moles of aluminum
Yeah, it's
to 2 moles of iron, 2 moles of aluminum, and that gives us 3.673 moles of iron.
Okay.
Okay?
Like 6.
All right, so we're at 3:30,
This is
and why don't you guys start working on these on your own?
because you
and
need to
Ask questions as you need to. Right? So, 'cause there's, how many problems are there? 7? Oh, 8.